As an operator in an industrial facility, you are responsible for the safe and efficient operation of the systems in your plant. To do your job, you have to understand how these systems operate and how they're controlled. One way to get this information is by using diagrams. A type of diagram you're likely to use is a piping and instrumentation diagram, also known as P&IDs. The information on P&IDs is helpful for learning about a new system, as well as for troubleshooting a familiar system. In addition, when P&IDs are revised because changes are made to systems, they are helpful for learning about system modifications. P&IDs are helpful for identifying instrumentation that is used to monitor and control conditions in process systems. P&IDs indicate whether instruments are located on a board in another area or near the equipment. A circle with a horizontal line through it represents a remote instrument, that is, an instrument that is mounted on a board in a remote location, such as in a control room. A circle without a line represents a local instrument that is mounted near the system it is associated with. A circle with two crossed lines is sometimes used to represent a transmitter. Transmitters are typically mounted locally. Sometimes an instrument symbol also contains an identification number that helps to distinguish it from similar instruments in other systems. Generally, all the symbols for the instruments in a control system will contain the same number. This is helpful for identifying all the instruments that belong to a particular system. P&IDs also provide information about the types of piping in a system and how each type is represented. Piping sizes are also noted on many P&IDs. Knowing the type of piping and its size can be useful for tracing a system in the plant. P&IDs for a water treatment system can be used to show how P&IDs can be utilized to learn how systems work and how they are controlled. To learn a system, it may be helpful to start with a block diagram to get an overview of the system. The water treatment system used as an example consists of a chemical mixing section, a clarifying section, and a clear well section. The inputs to the chemical mixing section are lime, alum, and treated water. This section produces an alum solution and a lime solution. The two solutions are sent to the clarifying section. Raw river water enters the system in the clarifying section, where it is mixed with the solutions from the chemical mixing section. The alum causes solid materials in the water to clump together so that they can be removed. The lime is used when the pH of the water is lower than normal. It raises the pH and makes the water less acidic. The clarified water enters the clear well section, where most of the remaining solid materials are removed. The treated water is then sent to a storage tank. One way to learn how this system works is to look at the P&IDs for each section. The chemical mixing section is actually made up of two separate chemical systems, an alum system and a lime system. The equipment in the lime system includes a dry lime hopper, a motor-driven shaker, and a mix tank and mixer. Lime is added to the hopper manually. The shaker dispenses the lime from the hopper into the mix tank. Treated water enters the system through piping and is fed to the mix tank. The line symbol indicates that the piping is made of copper. The mixer mixes the lime and water. The mixture then flows out of the mix tank through a rubber hose. A control system starts and stops the lime system based on the pH of the raw water from the river. The control system has an analyzer transmitter that measures the pH of the river water. This type of transmitter is sometimes represented by a square rather than by a circle. The transmitter sends an electrical signal to a pH recorder controller. The pH recorder controller records the pH of the raw river water. When the pH of the raw water is too low, the controller sends an electrical signal to a solenoid-operated control valve to the mixer motor, and to the motor on the lime shaker. The solenoid opens the valve to admit water to the tank, and the two motors start to operate. As treated water and dry lime enter the tank, the mixer mixes the water and lime. The mixture flows out of the tank to the clarifying section. The alum system makes a solution of alum and water. To make the solution, the operator first adjusts the flow recorder controller to close the alum solution control valve. Then the operator opens a valve to add a concentrated alum solution to the mixing tank. The alum storage tank is not shown on the P&ID. A note indicates the source of the alum. Using the sight glass on the tank, the operator monitors the level in the tank until the level corresponds to the amount needed to make a full tank of alum solution. The operator then adds treated water to fill the tank. The mixer in the tank stirs the solution. Then the operator adjusts the flow recorder controller to open the control valve. The flow of alum solution from the tank is regulated by the control valve based on the flow rate of river water entering the water treatment system. There is an orifice plate in the river water piping. A flow transmitter is connected by tubing to the piping on each side of the orifice plate. The transmitter compares the pressures on the two sides of the plate to determine the rate of flow in the pipe. The flow transmitter then sends a pneumatic signal to the flow recorder controller, and the recorder controller sends a pneumatic signal to the alum solution flow control valve. The valve regulates the flow of alum solution from the alum mixing tank to the clarifying section. The line symbol indicates that the alum solution piping is made of PVC plastic. If a test shows that the wrong amount of alum is being sent to the clarifying section, the operator adjusts the flow recorder controller. This changes the flow through the alum solution flow control valve to correct the problem. The alum solution and the lime solution flow to the clarifying section, as the notes on the diagram indicate. The clarifying section consists of a single vessel with 3 compartments: a flash mixer, a flocculation basin, and a sedimentation basin. Raw river water enters the system in the flash mixer, where it is mixed with alum and lime from the chemical mixing section. The alum causes suspended solid material in the water to begin to clump together. The lime is used to raise the pH of the water when the pH is lower than normal. The flash mixer compartment contains a motor-operated mixer. An analyzer transmitter measures the pH of the water in the flash mixer. The analyzer transmitter is connected to a pH indicator recorder. The mixture of water and chemicals in the flash mixer overflows a weir and enters the flocculation basin. In the flocculation basin, the water and chemicals are stirred gently by a large mixer, and the clumps of solid material grow larger. The water and solids then overflow another weir into the sedimentation basin. In the sedimentation basin, the clumps of suspended solids settle out and form a sludge on the bottom of the basin. A motor-operated sludge rake moves the sludge to a trough at one end of the basin where it can be removed. A level transmitter senses the level in the basin and sends a signal to a level recorder controller. The recorder controller sends a pneumatic signal to the positioner on a control valve. The valve controls the level in the sedimentation basin by regulating the flow of river water that enters the clarifying section at the flash mixer. From the sedimentation basin, the clarified water leaves the clarifying section and goes to the clear well section. The major components in the clear well section are a gravity filter and a clear well. The gravity filter removes the small amount of solids that have not settled out. A pressure differential transmitter receives pressure signals from 2 connections on the filter and produces a pneumatic signal that is proportional to the difference in pressure across the filter. The transmitter signal goes to a remote pressure differential indicator. When the difference in the pressures measured at the two pressure connections on the filter reaches a predetermined value, it means that the filter has become clogged by trapped materials. When this happens, the filter must be taken out of service so that it can be cleaned. To clean the filter, an isolation valve is closed to stop flow into the clear well, and the filter is backwashed with treated water to remove the trapped material. Then the filter is returned to service. If the water level in the filter drops below a certain level, a level switch sends an electrical signal to a motor-operated gate valve. The valve then closes to stop valve. The valve filter. If the filter runs dry, it will not work properly. The symbols labeled FR and FT represent the components of an instrument system that records the flow of water to the clear well section. The clear well holds the treated water until it is sent to storage. The level in the clear well basin is sensed by a level transmitter. The level transmitter sends a pneumatic signal to a level recorder controller. The recorder controller sends a signal to a pneumatic globe valve. The valve controls the flow of water into the clear well basin. From the clear well basin, the treated water leaves the system and goes to a storage tank. The problem to be considered is associated with the pH of the water in the clarifying section. An analysis of the water in the clarifying section shows that the pH of the water is not being adjusted properly. If the problem is not corrected, the process that uses the water from this system will be affected. Since the problem involves the pH of the water, troubleshooting begins with checking things that could affect the pH. The P&ID for the clarifying section is helpful in determining what these things are. In the clarifying section, attention is focused on the flash mixer because that is where the pH is adjusted by the addition of the lime solution. The analyzer transmitter measures the pH of the water in the flash mixer and sends a signal that represents the pH to a pH indicator recorder. The pH indicator recorder is indicating that the pH of the water is too low. The P&ID can be used to identify the equipment that could malfunction and cause the pH to be lower than it should be. For example, the P&ID indicates that the lime solution from the chemical mixing section is carried to the flash mixer by a rubber hose. Check the hose to make sure that it is not clogged or leaking. If the hose is okay, a logical next step is to check the components at the other end of the hose, in the system that makes the lime solution. It is common to have trace flows upstream to other systems to locate the causes of problems. This often means that more than one P&ID may be needed to troubleshoot a problem. In this example, the P&ID for the chemical mixing section is needed. The lime solution carried by the hose is made in the mix tank of the lime system, so the tank and its motor-driven mixer could be checked for visible problems. Lime is added to the mix tank by a motor-driven shaker, so the shaker could be checked to see if it is clogged or damaged. The motor could also be checked for problems. Lime for the shaker comes from a hopper that is filled manually, so another thing to check is whether the hopper contains a supply of lime. Treated water used to make the solution is added by opening a control valve in the treated water supply line, so the valve could be checked for proper operation. Since the system is controlled by a pH recorder controller, that controller could also be checked. Finally, the electrical conduits could be traced from the lime system to the pH recorder controller and back to the analyzer transmitter, looking for damage that might indicate an electrical signal problem. After the components that could be causing the problem have been identified, they can be inspected to locate the problem. In the example, the problem was caused by a bad electrical connection at the lime shaker motor that kept the motor from operating properly. The problem to be considered is associated with a water deaerator system that is designed to remove dissolved oxygen and other gases from a supply of water. The deaerated water is sent to a storage tank and then fed to a boiler. The P&ID for the deaerator system is helpful in understanding how the system operates. Water that enters this system is first heated by steam in a heat exchanger. A local temperature indicator indicates the temperature of the water leaving the heat exchanger. Next, the water flows through an arrangement of valves. One of the valves is a level control valve that controls the level in the storage tank. From the valves, the water enters the deaerator. Steam is supplied to the deaerator through a gate valve. In the deaerator, the steam strips dissolved gases from the water. The steam and gases leave the deaerator through a vent line, and the deaerated water flows out of the deaerator to the storage tank. The deaerated water storage tank has a temperature indicator, a level gauge, and a level transmitter. The level transmitter is connected to a level controller and to a level alarm system. The controller is connected to the deaerator level control valve that regulates the flow of water into the deaerator. The level alarm system includes two level switches that are connected by electrical signal lines to a remote level alarm. If the level in the storage tank gets too high or too low, one of the level switches activates the alarm. The deaerated water leaves the storage tank through a line at the bottom of the tank. The problem being considered is that the level alarm on the deaerated water storage tank has been activated, indicating that the level in the tank is either too high or too low. The first step in troubleshooting the problem is to check the level gauge on the tank to see what the level actually is. In the example, when the level gauge on the storage tank was checked, the level was found to be within normal limits. The next step is to consider the possible causes of a false level alarm. The P&ID is helpful in identifying the components that could cause the alarm to incorrectly indicate a level problem in the tank. One of these components is the level transmitter. If there is a problem in the transmitter could send a false signal to the other instruments in the level control system. The pneumatic lines that connect the instruments in the level control system can be checked for leaks or damage that could interfere with the signal transmission. The low-level switch and the high-level switch should be checked to see if they are working properly. Since the level alarm has been activated, the level alarm and its connections to the level switches are probably in good working order. In the example, when the components in the system were checked, the problem turned out to be a faulty level transmitter that sent a false high-level signal to the rest of the components in the control system. In this case, the alarm alerted personnel to a problem early enough so that they were able to locate the problem before it had a major effect on the operation of the system. If the problem had not been found quickly, the false high-level signal from the transmitter would have caused the level controller to close the control valve, reducing or stopping the flow of water into the deaerator and the storage tank. As an operator in an industrial facility, you are responsible for the safe and efficient operation of the systems in your plant. And to do your job, you must understand how these systems operate and how they're controlled. The information on P&IDs is helpful for learning about a new system, as well as for troubleshooting a familiar system.